Okay, David, it's 12:30. Should we?
Yeah, take it away.
Okay, so it's my pleasure to introduce Dave Albonesi, who's our keynote speaker. I got to know Dave first as a member of his PhD committee back in the 1990s, and in his early research, he was one of the leading proponents of dynamic voltage and frequency scaling and low power architectures, and also simplified architectures, and also went on to work in optical interconnects for chip multiprocessors, and has since done work in GPU architectures, and he's also lately gotten interested in smart buildings. So what got us excited about having Dave do the keynote was the fact that he had done this. Originally taken a regular class and turned it into a MOOC for first-year students, in which the foundation of it is using smartphones, and looking at the technology in smartphones as a way of introducing first-year students to computing technology. And of course, smartphones now are both parallel and distributed in the technologies that they use. And so they present a wonderful opportunity to show students the landscape of what real computing looks like these days, as opposed to sort of our traditional sequential von Neumann approach that's taken in many introductory course sequences. So we thought it would be really fantastic to have Dave come and talk about his experience introducing this material, and how it's gone with first-year students, and what he's learned from that. So without further ado, I'm going to turn it over to Dave to tell us about his experience with this class. Thank you. Dave,
right.
Good.
Thank you, Chip, and thank you to the organizing committee for this invitation, and all of you for coming. For this discussion of what began as a solo project, really in 2010, with about 15 students, and has since evolved over time with the help of many dedicated Cornell staff and students into a course that's upwards of now 200 students, which makes it the most popular ENGRI class in the College of Engineering. Now, this is a segue into my next slide, which is, why did I develop this course? Well, the answer is pretty simple. And that was, there was this lack of introduction to engineering courses in computer engineering. So every Cornell freshman has to take one of these ENGRI courses, and they range in topics from nanotechnology to computing and the arts. But there was this void that I saw in computer engineering. And so I wanted to get freshmen from the beginning interested in hardware. So that was my objective. The other objectives were, first of all, I just want them to understand the operation of computer system hardware and software and their interaction. What this means is understanding the stack of computer systems. So starting from numbers and transistors and all the way up to software. So understanding from the freshman year, the stack and all the layers, and so they could understand this interaction. So give them the understanding of the interaction of the stack, all the layers from transistors all the way up to software. The second is to gain some insight into the hardware architecture of smartphones, laptops, and supercomputers. So I showed them early on, here's an Apple, it was an A4 chip at the time in a smartphone. Here's an Intel chip in a laptop. Here's an AMD chip in a Cray supercomputer. And so I wanted them to see there's some similarities here, and it's all about engineering trade-offs in terms of the decisions they're making that you're making with these different machines. The third is I wanted them to understand high-performance hardware parallelism techniques. I wanted to introduce them to instruction-level parallelism, thread-level parallelism, data-level parallelism. And then, to motivate further study in the field. Frankly, a lot of us who teach these ENGRI courses are trying to attract students into the major, right? So I'm trying to, a student who's on the fence, get them excited about this. Honestly, sorry for all you computer scientists out there, but I'm trying to also, say, hey, if you're a CS major, hardware stuff's pretty cool too. You might be able to get the best of both worlds. So, all of us who are teaching these courses are trying to get students interested in the major. In terms of the evolution of the course, so the the initial 2010 offering was a lecture style, and I taught it for a couple more years, and then I went off to another teaching assignment. But then, almost on a whim, I submitted this for a MOOC. So in 2014, Cornell was soliciting proposals. They were going to pick 4 courses. I sent mine in, and it was selected. So then, the fun began. So then we had to figure out, okay, we have this now wide audience. I think this large group of students, tens of thousands of students participate in these MOOCs. So how do we target this audience? So how do we simplify things? And what should be our focus? And it became pretty clear that the focus should be the smartphone, right? A supercomputer is this esoteric thing, but everyone has a smartphone, everyone can hold it in their hands. And so we came up with this title of the computing technology inside your smartphone. And then we went through and we developed all these videos, these things called check your understanding questions, which I'll discuss, these homework questions. We had these labs. I'll talk about these labs that we did. And we have some interviews, which I won't have time to talk about, but they're kind of interesting. And the course was offered to over 17,000 students from around the world, which is kind of small by MOOC standards, but still pretty large. And what was gratifying is that 93% of those surveyed said they would recommend it to a friend or family member, which was pretty good. We were pretty happy with that. And actually, I could show you all the comments, but we had lots of very, very positive comments. Students were generally very, very satisfied with the course. Well, it wasn't all work and no play, so I want to explain this slide. So as I'll show you at the end of a module, I'll tell you what a module is. I came up with this thing called let's get into it. So at the end of a module, I say, let's get into it. And I just came up with that. So the videographer, Derek, he found the worst possible frame that he could find of let's get into it. So he sent this picture of me like this, and he sent this image, and he sent it to me with the title T-shirt. So he sent this thing, he named it T-shirt. So true to form, I went to the local T-shirt place. I made all these T-shirts for everybody who was involved, and I gave everybody a T-shirt. So that was the fun part of doing this. But some of the lessons that were learned, in the first is, and I can't overemphasize this, when you're attracting a wide audience, we had 125 countries who were tuning in. Now, not everybody finished, of course, but there were a lot of people out there. We really need to simplify. And I was fortunate to have behind the camera a historian and a mechanical engineer. And they were my checks and balances. So they were the people who said, that was pretty complicated. Can you try to simplify it? Can you maybe try this, right? So we really had to make this really simple. It's a complex topic. We really had to simplify. And, you can see me look at the camera. Sometimes I'm looking and teaching to them, right? So I'm trying to teach to a historian. I'm trying to teach to a mechanical engineer. So we really needed to simplify. The second is we made very extensive use of visuals. And you see these in some of the videos. We don't overdo it, but I think we do it just about right. And the third thing is to not cut corners and to get it right. So we tried for perfection. We didn't get there, but we redid videos a lot. So we did different angles. I have this kind of freelancing thing that I did. We redid those a lot. So we tried to get it as best as we could. And the last thing, is kind of cliche, but really enjoy the experience. If you're going to do these kind of courses, you really have to enjoy it. And I made, I couldn't say long-lasting friendships, but very friendly relations with everybody who was in the studio. Now, as it turns out, in 2017, the director of undergraduate studies said, can you teach the freshman class again? And actually, I should have anticipated this, but I didn't expect it. So I made use of all of the MOOC materials, right? We took all of those materials that we painstakingly created, and we made use of those. Now, students, what they do is they sign up for a special edX class, and it's called EDGE, and it's specific to Cornell. By the way, we have created an EDGE class, and I'm going to give you a link at the end. So we've duplicated the class on EDGE. So you can create your own EDGE account. You can contact me. I can give you access to the course, and I'll talk about how to do that at the end. But I had to do something in the classroom. I had to do some classroom work now. And so what we did is this thing called flipping the classroom, and I'll talk a little bit more about that a little bit later on. And the motivation from the beginning, okay, was a system on chip in a smartphone. And this is a little bit dated. It's a Qualcomm Snapdragon 805. And actually the way I got access to this was the marketing manager for the Snapdragon line is a Cornell alum, who happens to be a Cornell ECE alum. So I reached out to him. He put me in touch with the engineers. They gave me all this information. Now they're about to discontinue it, so it really wasn't that advanced, but still I got a lot of information on this chip. And, you know, what we're emphasizing primarily in this chip is the multi-core processor, the apps processor. But I want to point out there's all of this specialized hardware, right? That there's this trend moving to specialization, things like multimedia and audio and the GPU. And what I teach now in the course is that we've got this specialized machine learning hardware, right? For object recognition, speech recognition. And, you know, I'm trying to attract students into hardware, right? So I'm telling them, you know, this specialized hardware for machine learning is now far faster, more energy efficient than software. And in fact, there's this graphic from Qualcomm that shows with their latest DSP, you can get a 25x improvement in energy efficiency and 8x over performance versus doing it on a general purpose CPU. So this is the early motivation. We're trying to motivate them to get excited about systems on a chip, about this apps processor. But we have to start from the beginning, right? These are freshmen. We have to start from the beginning. And so what we do is we develop this bottom-up understanding of a computer. And this picture, by the way, we put in like all of our videos. So this is the stack. And you know, we start at numbers and operations, go from transistors and gates, and go all the way up to C. And you know, we cover all of these layers eventually, right? We're getting up the stack on all these layers. So we're showing this picture, and then we show where we are in the stack in all of these videos. And so what we're developing is this bottom-up understanding of a computer. We're doing bits, data types, operations, digital logic, microarchitecture, right? All of these topics. We talk about C. Now, by no means is this a full course in C, but enough C so that they can say, take a for loop and become the compiler and create the LC3. And that's I'll talk about the LC3 assembly. And then, you know, that gets translated into bits. Right? So we're giving them enough C so they can make that connection. And the kind of cool thing that we have is this bottom-up design of a processor. So we have these hardware design labs, which are using Jade, which is a browser-based design tool from MIT. And I'll show you a few examples of this. I know this isn't like the parallelism part, but it's kind of cool to see how we can build up this processor from scratch. And it culminates in the design of this computer, which we call the LC3 Lite. It's a lighter version of the LC3 from Pat Patel. So Pat Patel had this thing called Little Computer 3. It's in their introductory textbook, Introduction to Computing Systems, which is designed for freshmen. We take this LC3 Lite and we strip that down. And also they can write these very simple assembly language programs. They can build up their LC3 and they can write these very simple assembly language programs. So this is the LC3 Lite. It's real simple. You know, it's got a register file, it's got an ALU, it's got the memory, it's got these other things. You know, the only thing it's missing is IO because we can't do input output in Jade, but of course we do discuss IO in the course. So that's kind of building up like the computing part. And then we talk about the parallelism part. So how do we make these smartphones fast? And, you know, we talk about all of these topics. We don't go into the great detail that you would in a more advanced class, but we talk about how do you measure performance. What's kind of neat is we made this pipeline version of the LC3. So we invented this LC3 pipeline. And when we talk about pipelining, we're relating it to the LC3, which is something that they understand. So we talk about how do you make a forwarding path, right, from here to here? How do you do that within the LC3 pipeline? Again, we're talking about superscalar, multi-threading vector parallelism. Cache is, of course, a very important topic. We talk about permanent storage, talk about paging, for instance. And then multiprocessing, multi-core, for instance, we cover cache coherence. All right, so I've been talking a lot. So I think everyone's kind of interested in seeing the course. So I want to give you some sampling of the course. And I'm going to now switch to my browser. So I want to show you kind of what we're going to go through. So I'm going to talk about the general organization. I'm going to show you an introductory video so you can kind of see kind of the graphics that we do. I'll talk about very briefly the labs using Jade, just because I think they're kind of cool. And then I'll talk about, there's 3 videos. So, if you want to create your own course, I'm showing you just kind of 3 styles of videos that we did. So there's this kind of free-form style that I do. There's a screen behind me, and then there's like annotating on a whiteboard. So these are kind of the 3 styles that maybe you want to think about incorporating into your own course. And then I'm going to talk about the multi-core module. And I'm going to talk about, kind of walk through the videos, and won't have time to really get through all of it. But I want to then use that as a motivation for how we do the flipped classroom experience. Okay, so I'm going to exit here. I'm going to stop sharing. And I'm now going to share my course. Let me see, tell me if you can see this. Can everybody see this? Everybody see the course? Great. Okay, so here's the general layout of the course. Okay, so we have this introduction, and then we have these main topics. We have digital logic, computer organization, programming, performance, and conclusion. And you can open up any of these, and you can get more details. So I just want to show you the introductory video so you kind of see how we're presenting the course and how we're motivating the course. So let me show you the introductory video, and I'm going to show this at a little faster speed than 1x. All right, so first of all, here's the overview. So here's what we're learning, right? So these are the overall learning outcomes, right? And the whole point is we're trying to make this really simple. We're trying to explain this in very simple terms, right? The different layers of computing technology within your smartphone, the hardware level, right? And then, here are the learning outcomes. And these are the things that actually, they will learn at the end of this course. Describe how a smartphone processor works. Explain computer systems design from binary to programming. They'll have designed a small computer, and then some design and some common techniques to make computers fast, right? So this is what they'll have learned by the end. So I'm going to show you, so this is a video, and it shows me with a screen in the back, and this is the whole introductory video. So let me show you this. And I got this a little fast, but I'm going to show it maybe even a little faster.
Now let's discuss what you're going to learn in this course. So the course is broken up into 3 big chunks. And in the first part, we're going to learn the operation of computer systems hardware and software and how they interact. Now we're going to learn everything from transistors to logic gates to the way computers are organized, instructions to software. And very importantly, we're going to discuss how the hardware and software interact, how they come together in what's called the instruction set architecture. Now, the second big part of the course is advanced performance techniques. Once we've got the fundamentals of hardware and software behind us, we're going to be prepared to look at the techniques that computer architects use to make your smartphone run so fast. And then the last part of the course, once we've learned this, is to look at the design of actual smartphone processors. And we're going to look at the Qualcomm Snapdragon processor, which many of you carry around with you every day. After we take a look inside a smartphone and cover a couple of big ideas in computing systems, then we're going to move step by step to the computing technology stack. And here's a picture of that. So this is broken up into 3 big pieces: digital logic, computer organization, and programming. And we're going to start at the bottom at transistors and gates, and also talk about numbers. And then we're going to move through digital logic, which will give us some skills that we can then apply to the design of a computer. And that's the computer organization part of the computing technology stack. After that, we're going to move on to programming. We're going to see software, and we're going to see how these all fit together in the end. After we've learned about the hardware software stack, we'll be prepared to cover advanced performance techniques that computer architects use to make our smartphones work so fast. And there's a number of techniques that we're going to cover, including pipelining, where we use an assembly line of instruction execution, superscalar, where we execute multiple instructions at the same time, multi-threading, where we may execute multiple programs within our processor at the same time, SIMD, or single instruction multiple data, which is a way to get data level parallelism, which is very important in particular applications, caches, which make our memories fast, and then multi-core, which is putting multiple processors on a single chip. Then we'll be prepared to go into the details of actual smartphone processors. Now we're going to focus on the Qualcomm Snapdragon, which is used in many Android phones. So if you have an Android phone, there's a pretty good chance you've got a Snapdragon chip in there. Now here's a diagram of the system on chip, or the SoC, for the Snapdragon 805. Now we're going to go over this SoC in a little bit of detail, we're going to go into great detail on the apps processors. These are the main processor that runs your apps. Then we'll go into the details of the crate processor that's found in Snapdragon chips. Here's a block diagram. Now, this may be very complicated to you now, but after you've completed the course, you'll have a detailed understanding of the hardware design of this apps processor. Now, we're also going to do a lot of engineering design in this course. In the first part, we're going to design digital logic, things like adders and multiplexers and registers and finite state machines. Then we'll put those components together to create a working computer. And you're actually going to verify that your computer works properly by running programs on it. Now that we've seen an overview of the course, let's look inside a smartphone.
Okay, so that's the introduction. That's motivating, getting students excited about the class. Okay. Right, so the next thing I want to talk about is these labs that we've created. And so this is the first lab that students would do. And we have these general instructions that they have, and we use this design tool called Jade. And so to cut to the chase, here's a window, a Jade window. And what students can do is they can drag these components over here. So this student has dragged this component here, and we've created a 4-input OR gate. Now, the next thing we can do is we can use those components in future designs, right? And so we're building up with Jade, we're building up to something like a register file. So once we've designed all of these different components, we can create a register file. So we have a decoder here, we have all these registers, we have these multiplexers, so we can design this register file. And ultimately, what we're ending up with is the final LC3 Lite design. So this is the LC3 Lite that we introduced earlier in the course. And we provide the memory because it has the programs in it. We also provide them the finite state machine. There's an optional lab where they can do the finite state machine. We give them all the details. And so once we've consolidated, we basically consolidate all these components, then we create this pretty compact design that is the LC3 Lite. And the key thing is to run test programs on these. So we have these test programs that we have, and students are waiting, and they're waiting, and they're waiting, and they see that it passed, and everyone's excited. All right, so that's the labs using Jade. All right, so the next thing I want to talk about is the 3 styles of videos that we have. And the first thing I want to talk about is we start out every module. So this is, first of all, this is, within the course, this is the performance part of the course. This is the instruction level parallelism part of the course. And then we have this in this module, which introduces the course. And then we have these other tabs that you can go to get more additional information. Okay, so again, this is, we're trying to simplify the description here. We're talking about superscalar execution, a method that improves processor performance by taking advantage of a concept called instruction level parallelism. And then we explain what ILP is and the learning outcomes. So these are the learning outcomes. So at the end of the module, students will have explain and evaluate the operation and performance benefits as a superscalar pipeline versus non-superscalar, be able to look at a piece of code and examine the data dependencies, also look at a set of data dependent instructions and propose methods to avoid or mitigate the data dependencies, and then demonstrate the operation of an out of order processor, right? So we actually talk about an out of order processor with an issue queue, go into some details about that. So this is just an example of a free form type of lecture. And I will probably speed this up a little bit as we go. Okay, but I just want to give you an example of this kind of free form lecture. And here we're showing the stack, but we're showing instruction level parallelism.
Pipelining is one form of parallelism, where we perform multiple operations in the same time, in the same clock cycle. Now in our pipeline, in one clock cycle, we have 5 instructions that are in different stages of execution. Now in this module, we're going to expand our pipeline and make it a superscalar pipeline. In a superscalar pipeline, each of those pipeline stages can hold more than one instruction. So for instance, we can fetch 2 instructions in our program at the same time. We can decode those 2 instructions. We can execute those 2 instructions. And we can have each of our 5 pipeline stages be able to accommodate 2 instructions rather than 1. And this is exactly what your smartphone does. It has a superscalar pipeline, which may even be wider than 2 instructions. It may be able to, say, execute 4 instructions or even 6 instructions. Now, our superscalar pipeline, though, is going to be limited by the properties of our program. in particular, whether it has instruction level parallelism or ILP. So instruction level parallelism is the independence between different instructions in the same program. And what that implies is there's no data dependencies between instructions. So for instance, if I fetch those two instructions and there's a dependence between them, so if the first instruction writes a register that the second instruction reads, then when I get to execute, I can't execute them at the same time.
Right, so that gives you an idea of the kind of free-form discussion that we have. All right, so the next thing I want to talk about is this is now, and this is where we're going to have a test, by the way. Okay, so there's going to be some homework questions which you're going to have to answer. All right, and I'm going to show you another video where we're discussing thread level parallelism. And I've speeded this up to 1.5x.
Thread level parallelism, or TLP, refers to the parallelism among different threads. Now, a thread is a path of execution within a program. Now, each thread uses its own registers, but they share memory. Now, this is in contrast to two separate programs, such as our texting program and our browser program, which again have their own registers, but they have their own dedicated memory. So in either way, we have thread level parallelism between them. Let's consider two different threads that are ready to run. First of all, thread 1 is our loop program where we don't have any ILP. And thread 2, you see the same thing. It's a different program, but again, because of data dependencies, we don't have ILP. Now, later when we consider multi-core, we'll be able to run these threads on their own individual superscalar pipeline. What we're going to do instead is we're going to create a superscalar pipeline, a single core that can run them both at the same time. Here's our superscalar pipeline, which has been transformed to be a two-way multi-threaded pipeline. First of all, you'll notice that we've duplicated the PC. We now have two PCs. That's because we have two threads that each require their own PC. We also have shown the register file is divided into two register files. That's because each of the threads has its own independent registers. Now, in actuality, these two threads can share many of the pipeline resources. Although we've shown in EX that each ALU is dedicated to one thread, in a real design, both ALUs may be available to a single thread if it needs to use them. That's also the case for the memory stage. Although we've shown the data memories resources being separated among the two threads, in actuality, we may allow one thread to use all of the ports. The key feature here is that each of the threads has its own PC and its own independent set of registers. Now, again, the register file could be combined into one, and we may dynamically allocate registers to one thread or the other, but the threads won't interfere with each other. Now, this is one example of multithreading, which is called simultaneous multithreading, or SMT.
Okay, so SMT is kind of controversial. It's not necessarily found in all smartphones, like ARM smartphones that use them. I have an interview actually with Adam Karen, who is the product manager for the Qualcomm Snapdragon line, and he explains why they do not use SMT. Right, so I know the SMT is kind of controversial. It's not necessarily used in smartphones, so he explains why they don't use SMT. All right, so here is the homework assignment. Okay, so this would be a homework assignment that we would give to the students, and it's multiple choice, so it sounds kind of easy, but not necessarily. All right, so this is where we discuss this concept of register renaming. So register renaming is we take the logical registers, and through some mapping mechanism in the ID stage, we create some just greater physical registers. So for the LC3, which has 8 logical registers, we might create instead 16 registers. We might double that. And the reason to do that is because if I have two threads, right, I'm showing these two threads, they can have their own independent registers, right? So that's the whole idea behind register renaming. And so, okay, so here's a question, and I want you to put into the chat. Okay, I want you to put into the chat the answer, what you think the answer is. So as we say, instead of having two separate register files, one for each thread, we may implement a single register file and use this register renaming. And I actually discussed this earlier in the course in the instruction level parallelism part. To distinguish the registers in the two threads. For our two thread example, the logical registers might be renamed as follows. Okay, so you see that we have these unique registers. Okay, so here is the question. And I want you to tell me, is this 1, 2, 3, or 4? All right, so just put into the chat whether you think it's 1, 2, 3, or 4. Okay, so what this says is the first two instructions in each thread are in the EX stage. So which of the following describes the action that will be taken by the pipeline when those two instructions move into mem? So number 1, the second instruction in each of the two threads, not in add, will remain in ID for one additional cycle. Number 2, the second instruction in each of the two threads, not in add, will move into EX, but the third instruction in each thread and will remain in IF for one additional cycle. The second instruction in each of the two threads, not in add, will move together into EX, and the values of P1 and P7 will be bypassed from the mem stage. Or the second instruction of the two threads will move together into EX, but the values of P1 and P7 will not be bypassed from the mem stage. So what do you think it is? Do you think it is 1, 2, 3, or 4? Let's see what we get in the chat. I don't see any answers so far. All right, I see 1, 3. All right. All right, we got one answer of 3, and that is absolutely correct. So David is correct. So this explanation is a little bit short because it's talking about instruction-level parallelism, but it says as the two add instructions move into mem, the results P1 and P7 can be bypassed in the not and add as they move into EX. Okay, so that's the answer for that one. All right, very good. All right, so now I want to show you another form of lecture, which is a whiteboard lecture. And this is now we're talking about data hazards, right? So we're talking about pipeline, we have data hazards. And in the first video in part 1, we've kind of set the stage for this other lecture. So let me show you this. And I'm going to keep this at 1.5x.
Now that we've seen the overall idea behind forwarding, we're ready to make the modifications to our pipeline diagram. So here's a general diagram of our LC3 pipeline. And let's just review all the different stages. So first we have instruction fetch, where we read an instruction from the instruction memory. And then we have a set of flip-flops here. We have a register. It's a pipeline register. We just talked on the rising edge of the clock. So in the next tick of the clock, that instruction moves to decode. And in decode, we read the source registers. Next tick of the clock, we move into the execute stage, where for an operate instruction, we do the operation. For load or store, we calculate the address. Next tick of the clock, we get to the mem stage. And here, for load or store, we actually do the memory operation. And for other instructions, we just bypass the stage. And then finally, on the last tick of the clock here is the write back stage. Now what I've drawn here is I've actually drawn the connection back to the register file. So in our pipeline diagrams, we've had this other register over here, register file picture. But of course, we only have one register file. So I'm actually showing the real connection back to the one register file to do the write of the destination register. Now what I have here is I have our instruction sequence that we just saw. So let's just go over that again. So the first instruction in our sequence, and we're assuming that this is in the mem stage, is an add instruction, and that add writes to register 1. Right behind it is a not instruction that reads register 1. Now, it read this value of register 1 back here in ID. So it has the old value of register 1. It doesn't have this value, and this is our data hazard. This is our problem. Also, in the ID stage,
so I'm going to move ahead a little bit
for this value that's sitting here in that stage.
You know,
so in order to do that, we're going to just put a multiplexer. So we're going to add a multiplexer here. We still have this value because we may need it for other situations. And now we're going to take this value of R1 that we have here. Okay, so here we have the result of the add. We have it right here. And we're going to tap off that here. And we're going to feed that back here to this multiplexer. And so now we also need a select signal. And this will be part of our control now. This is an additional part of our control, is to pick the proper one of these two, okay, depending on what their dependence is among instructions in the pipeline.
Okay, so that's enough to do this. Now these are check your understanding questions. So these would be questions that students they'd watch the videos and then they answer these questions. Okay, so, all right, so here's another quiz. So let's look at this following piece of LC3 code. Okay, so first of all, this is the destination register and these are the source registers. Okay, that's the mnemonic here. Okay, so we have an add of R1, R2, R3. We have an AND of R4, R1, R2. And we have an LDR, so that's a load instruction, of R1, R4, and then &2. And so the question is, which of the following statements describes the forwarding that would occur within the pipeline in order to properly execute this code? You must check all that apply, okay? So I'm gonna say these are 1, 2, 3, and 4, so it might be 1 and 3 or 1 and 4 or whatever. So you have to put, all that apply. So first, the AND would be forwarded to the result of R1 from the add. The AND would be forwarded the result of R2 from the add. The LDR would be forwarded the result of R1 from the add. The LDR would be forwarded the result of R4 from the add. Okay, so 1, 2, 3, and 4. So let's put into the chat, what you put, what you think the answer is. Okay. All right, excellent. Yes, that is the answer. So here is the answer, and here is the explanation. I won't go into detail of the explanation, but one of the things that students can do actually they got a couple of tries on all of these problems, right? They got a couple of tries, and they can always look at the explanation for the answer. All right, here's another question. So this is the second CYU question. Consider the following LC3 code segment. We have add R1 and a not R1, R1, add R1, R2, R3, not R1, R1, and then and R5, R1, R6. So which of the following statements describes how the pipeline would handle forwarding in this case? First is that R1 from the add will get forward to both the not and the and. R1 from the add will get forwarded to the not, and R1 from the not will get forwarded to the and. R1 from the not will get forwarded to both the add and the and, or no forwarding would occur in this case. Okay, so what is the answer? All right. You're all acing this. 2. Okay, so 2 is the answer, and here is the explanation. Okay. All right, very good. All right, so the next thing I want to do is I want to discuss the multi-core module. And what I want to do is I want to show how we would do the flipped classroom approach. So I'm going to briefly talk about the multi-core module, show you the problems that they would do, and importantly, show the kind of feedback that they would provide to us. And then what we would do in the classroom the next day. So what students are required to do is they would watch these videos. So first of all, introducing multi-core. I'll cut to the chase here. I talk about how power consumption is a huge problem, right? So I don't just talk about performance in this. I talk about how we have these really deep pipelines, and with the combination of high frequency and all these registers, we had this power consumption problem. We had to shift to multi-core. So that's cutting to the chase on this introductory video. So, so this is the introductory video. And then I talk about general multiprocessing and multi-core, what multiprocessors are, what a multi-core is. There's these check your understanding questions. So they would have done these check your understanding questions. And then I talk about actual cache coherence. So we use this as our baseline. So we don't use an L2 cache. I introduce L2 caches in the videos, but we don't use an L2 cache for this particular example. So we use this, processor cache and memory as the baseline, and we discuss. So I discuss cache coherence. So I talk about the general problem of cache coherence, right? And then they do these check your understanding questions, and then finally I talk about the messy protocol and the messy solution, right? So they've done all these CYUs. They've done all these. They've answered the CYUs. They've finished. Before class. That's the whole key. They can finish before class. And then what they do is they provide this feedback. So I get this feedback, this multi-core feedback, and they go to this link, and it's a very simple Qualtrics survey. Let me know what topics or questions you like covered in our next class meeting, right? So then, then I look at this feedback, and that helps me provide for the lecture the next day. Now I'm going to stop sharing this screen and go back now to my slides. Let's just go back to the slides. All right. Okay, so how do we flip the classroom? Well, we're fortunate to have a classroom at Cornell that has this it's for small group problem solving. So these small tables, students sit around the classroom. And as I mentioned, the students watch the videos and they answer these CYU questions by 11 p.m. Before class. And then they provide feedback through that link. Now during lecture, what I'm trying to do is I'm trying to reinforce the material, because when I get these questions, some people say, I didn't understand the messy protocol or something like that. So I'm trying to reinforce the material, but I'm also trying to provide enhancement of the subject matter. I wanted to take it a step further than what they've learned in the videos. Now my TAs, they spoon feed problems to the students and to work on in small groups, and they monitor their tables. The TAs are walking around, I'm walking around monitoring these tables. And then what's interesting is what we do is we have one student from a designated hot seat table present their solution. So in normal times, we had an overhead projector. We don't have that today. because things are different today, but we would have an overhead projector. We give them hard copies. Student come up, will present their solution. So they present the solution rather than me, gives them some public speaking skills. So this would be a typical lecture that I would give the next day, right? So this is multi-core. This is a typical lecture I would give the next day. And, you know, I talk about SMT, I talk about multi-core, and, you know, this is the actual lecture. I'm not going to give you all of the, you know, all of the total details of this, but I'm also trying to relate this back to the Snapdragon SoC. So this is actually the multi-core. It's actually my own depiction of the multi-core, but this is the multi-core chip that's within the Snapdragon that the engineers told me about. All right, and now I mentioned that multi-core does not come for free, and that there's three major issues. There's consistency and synchronization, and all these asterisk things are things that they don't need to know now, but that they can learn later. And so I'm really focusing on the cache coherence problem. In the cache coherence problem, talk about this problem of multiple copies of the same data, and then the write by one processor makes copies stale, cache is no longer coherent. So I give this example, and this is an example that we also go over in the videos. We're loading a block from cache, block A from memory into the cache. Second one loads that. First one does a store operation, and now we have this inconsistent copies. And normally I would be annotating, so I'd have my iPad and I would be annotating and showing all of these things. Okay, so now I'm going a little bit more into depth about the protocol, you know, going a little bit more about what do these states mean? What does the modified state mean? What is the exclusive state, the shared and the invalid? But I also point out that all of this is really completely managed by hardware, right? This is something that hardware completely manages. And then I'm going into, you know, the rules, and it's, you know, it's pretty complicated, right? This is pretty complicated stuff. So I'm walking through this pretty slowly, right, about the rules. And this is just a subset of the rules about this idea that you need to invalidate other copies. You have this special invalidate message, that we snoop, you know, operations. And then if you have a modified copy, you need to provide it, right? So I'm going through kind of step by step, pretty slowly through these rules, trying to use simplified language as much as possible. And then we go back to that previous example with the messy solution of how we would, you know, solve that problem. Okay, and then here's what I'm trying to do. I'm trying to now tie a bunch of pieces together, right? So I'm actually starting with a piece of C code. And this is a very contrived example, as you see, right? This code really, you know, really doesn't do much, but it's a contrived, it's an example that's trying to get them to connect the layers from C all the way down to cache coherence. And so we start with this for loop, and I say, let's break this up into two threads, right? So thread one is running on processor one, and it does this multiplication by 2. And then thread 2 is doing the B plus I, and thread 2 is responsible for doing the final result. And so there needs to be some communication from thread 1 to thread 2 to get the final result. And so what we do is we say, okay, well, let's look at the assembly code for each of these. And they know by now how to take a for loop and to write the assembly code for it. So we break this down into the assembly. And the key thing here is that the store, the last store, right, has to be communicated to thread 2. So the third operation from the bottom is a load, and so we need to load that. And by the way, this memory at the right, this 4000, 4001, 4002, that's what we designate as the data memory within the LC3 light, right? So that's where all of our data is stored. Okay. All right, so you know they know how to do this for loop. This is the code that we have, and then what we say, okay, let's do this problem where and A and B are in the same cache block, and we're doing cache coherence using messy. And so we give them this problem. So this is the problem that we give, and they're sitting around tables and they're brainstorming around the tables about this problem. And you know, the answer to A, and I'll give you the answers, but the answer to A is that communication problem, right? Is that communication problem, right? Without cache coherence, you can't get the result. We'd only write from processor 1, we'd only write to the cache. And B, you know, requires them to fill in the table. So they fill in the table with all the hits and misses for all of the loads and stores associated with the different threads. Now, I punt a bit on synchronization by saying that processor 1 has priority for the interconnection network, right? So processor 1 is running a little bit ahead of processor 2, so that's why we're able to do that store to A before we do the load of A. But the answer, this is what turns out to be the answer. And, a student will come up and students will by and large get the answer. So this is the answer that the store of A in thread 1 will only write to processor 1's cache, and load of A in thread 2 will read the old stale copy. And they will fill out this table of the messy protocol. So this is an attempt to start with, the high-level language statement, get this down to assembly, and then relate this to cache coherence. All right, so let's talk about some metrics. So if I look at the student evaluations from 2020, which was last spring, which is the most recent offering of the course, versus 2012, which is the last offering of the lecture style class. Now there's a big difference in responses. There were 120 in 2020 versus 43 in 2012. So interestingly, the teaching effectiveness was 1.3x improvement, but overall course was 1.1. I think what that means, and I have some evidence to prove this from the feedback, is that it was hard. The overall course, generally students like my courses, but I think for the 2012 course, it was really hard to grasp a lot of the material. So that kind of affected my teaching effectiveness. Now the student feedback from 2020 was pretty positive. I'm throwing in some not so positive comments, but it was pretty positive. So the student said I was amazed at how much that I, with minimal EC experience, was able to learn. And they pointed out that the format edX allowed me to ask questions ahead of lecture. This other student, second student, mentions the problems discussed in class really helped. This other student, and it's overwhelming for a lot of students. I mean, this is a lot of material. And the student talked about how they covered a lot of material. There's a lot of memorization, and it is a pretty jam-packed course. This particular student, the fourth student, liked the course on programming and how it connected down through the entire stack. This other student joined the flipped classroom. This one student thought the in-class discussions were annoying. And actually, one of the problems is that, you're picking a hot seat table, but other students are finished first. And so, there's kind of this delay. And so that person found that annoying. Another student thought these were a little drawn out on a tangent. The ideas were introduced again too quickly. Generally delivered well, wish it could be covered more slowly. And last two students really enjoyed working through the problems in class, and using edX is a great idea. And I think it really helped me understand the material. So generally positive feedback. All right, so I want to talk to you about my future plans. So I have some updates coming in fall 2021. So I really need to redo these videos were made in 2015. Of course, a lot has changed in 2015. There are certain videos which I felt didn't come out very well, which I want to redo, but I really have to address the SoC. I really have to update with a modern processor. Now, the other thing I'm going to do is the classroom material. So I'm going to kind of reproduce what we do in the class. So I'm going to record the in-person lectures, and I'm going to make available the in-class handouts and solutions. So this is so that another professor at Cornell could potentially teach the class. But also I'm thinking I may make this available if you're interested in this class. I mean, I have the rights to this class. If you're interested in this class and in using these materials, then contact me and I could potentially make them available to you. I have to check with my department, make sure that's okay. I think that the people who did the videos are fine with it. I have to check with my department, but I could potentially make all of this material available to you if it's something that you want to teach. Of course, the caveat is edX, right? So all this stuff is on edX, so that's the caveat. But contact me if you think you may be interested. In terms of acknowledgements, tremendous amount of help from people from the Center for Teaching Excellence. Diane Sempler was the main person involved. Rob Vanderlyn was that historian who was there in the studio who helped me out. Course development, Patrice was the mechanical engineer. and Mike also did a lot of the development. The audio video was Serge Derrick. Derrick was the guy who captured that frame, and Colbert, who did the audio. Had some great TAs at the very beginning. So these are the people who started, who really got this course off the ground. So KK, he was a PhD student who did a lot of the work on the course. He found Jade, for instance, and then Udit Gulnar and Ava did a tremendous amount of work. I actually had a coach. They actually sent me to this person, Eliza Van Court, to practice. So I had her as a coach. And some recent contributors are Julie, who's been doing a lot of work lately, and there's just been numerous TAs throughout the years who've helped me with the course. All right, so here's how to access the edX course. So here's the link. You'll be prompted to create an edX Edge account. So you should create an Edge account, not an EDX account. So edge.edx.org is what you should do. Once you enroll, contact me. Now, I can't guarantee that I'm going to be able to get this really quickly. It may take me a few weeks, but I will make sure that I enroll you. But please keep in mind that the materials are copyrighted and don't share those with others. Okay, so that's all I have. Thank you for your time, and I'd be happy to take any questions.
Excellent, thank you. We have about 10 minutes for questions. So please, if you have some questions, please put them in the chat, and I'll try to keep up. Oh, actually, we have our first one here. So, given that so many SBCs contain the same processors as smartphones, do you have any plans to incorporate SBCs into your course?
That's a really interesting thought. At the moment, I don't. But I will. I mean, it's something certainly to consider. But I haven't thought about that. That's a really interesting question, interesting thought.
So for myself, I was really impressed by your what are they called, the check your understanding questions. Those are sort of, I mean, I think of those as clicker questions, but that kind of material, it seems like it's sort of hard to come up with questions. What was your process for coming up with those?
Yeah, it was, yeah, I came up with all of those questions. It was, yeah, doing a multiple choice it's tricky to come up with questions that are challenging.
Mm-hmm.
I guess it was just, I just kind of brainstormed and just thought of, okay, this option, and I thought about other options. So just kind of, I guess it kind of came naturally, but yeah, my thought process was really just coming up with an answer, for instance, that sounded, I guess, coming up with an answer that sounded enticing, right? So that's the thing with a multiple choice question. Like there's some of them that are like, that sounds about right, right? So trying to get an answer in there that would sound enticing but is incorrect, right? So that was part of my thought process.
Okay, from the audience here, so has the impact of this course on downstream courses been studied, right? So people that take your courses, are they different somehow in later courses?
So what do you mean by a downstream?
This next course, or 2 courses later.
Yeah. So actually, when we created the course, we actually put a lot of digital logic content, right? We put a lot of digital logic stuff in there, and because we were creating a MOOC, right? And so we were trying to put all of this digital stuff in there, and it turns out that students who take my course actually have an advantage for the next course, which is EC 2300, and that's actually somewhat, I would say it's somewhat intentional. I think if students see something multiple times, right? Mm-hmm. It's good for that. It's good for them to see something multiple times. So I really don't have a problem with that, of students having my course and then going into the next course, which is a digital logic course, because they don't always remember it, and it just, when they see it again, it'll be additional reinforcement.
Your overall approach is kind of bottom up, right? You're starting with gates. What are the sort of advantages and disadvantages of this pedagogically, right? Versus a, start at the top and come down.
Advantages, disadvantages.
What, did you consider doing a top-down course?
I didn't, and the reason that I didn't, actually the reason I didn't is because I adopted this textbook from Pat Patel. And the Pat Patel textbook, which is Introduction to Computing Systems from Bits and C to Programming Beyond or something like that, right? It starts from the bottom up. So, so I started from the bottom up. Yeah. I don't know, if it really would make a whole lot of difference if you start from the top down, if you start from programming and made your way down. It's just what I did was a bottom-up approach, but if you started from programming and then you went to assembly, right?
Mm-hmm.
And then you introduced instruction set architecture, right? Seems to me that could be a viable approach as well, right? Starting from programming to assembly, instruction set architecture, and then you got to get down to some of the nitty-gritty details slowly, right? Digital logic and down. That seems to be a viable approach as well.
So then there's one about the using smartphones as your basis here. So I was actually thinking about, how was your retention in the MOOC, right? A lot of these courses start big and shrink down a lot.
Yes.
Do you think tying it to smartphones, helps that, or are students disappointed when they realize, oh, we actually have to do other stuff first? Or
I think what happened was the title is very enticing.
Mm-hmm.
The computing technology inside your smartphone. So a lot of people signed up and they didn't know what they were getting into. I mean, you see this course, right? It's a very intense course.
Yeah.
But although we had over 17,000 students, we had a very, very much smaller number who actually got through the course, the entire course. They realized this, quickly, a lot of them realized that this was a pretty intense course and dropped out. So I don't think it was, oh, we're learning about digital organization, it's not really smartphones. I think it was like a big barrier to entry for them to take this course and to get through it. I think that was one of the big problems and why we had a much smaller retention rate.
What about your Cornell students, right? So they're kind of stuck in the course much more firmly, right? Is retention similar to other of these, whatever the intro courses were called?
Yeah, I found it's about the same. I found that, for example, I teach two courses. I teach this course. I also teach digital logic computer organization, and I found that that there's really not a big difference in terms of the number of students who drop out. So I think that the retention rate is reasonable. Is about the same as what you would see in a sophomore level digital logic computer organization course.
Okay, and I think we have time for a last question here. Did you have sections about how phones rely on digital services, right? So cloud storage or device synchronization?
Yeah, good question, Chip. No, I don't. The focus of the course is really about, rather than Wi-Fi service and things like that, was really, it was a focus on computer engineering is really what the focus of the course was, right? So that was what I was trying to achieve, was a course that focused more on the computer engineering part of the course, rather than cloud storage, device synchronization, things like that.
Well, thank you very much. That was a very good talk. And that's a very intense course. Like, I was trying to figure out the answers to your questions.
Well, you did a great job. I think you got 100%.
Yeah, thanks. But
right.
Yes, okay. So
thank you, everybody.
Let's thank the speaker again. Doesn't work so well without audio, but But thank you very
Right.
much for coming and giving us this talk.
Right. Thanks. Bye, everybody.
Thank you. This was really good.
So, and we do actually have a break scheduled now. And so you got 15 minutes. We'll resume at 10:45 Pacific time, and that will be going into the first paper session. So everybody go take a walk around. Thank you.